In this clip, we will look at another application of breadth first search. Recall that when you use breadth first search, the tree that you have that return from the breadth first search is the shortest path tree when each edge is of length 1. Okay, so because you work in layers, right? So if you are in this layer, it means that the shortest path from the source to you is this long, right? This is the shortest path. Okay, when each edge, when you think of each edge has a length of 1. Okay, so that's one key application of breadth first search, and you've been using it in some other tasks. There's another one important application of breadth first search. This is for testing a bipartite graph. But so let's have a quick review. Okay, so let's look at this problem. So you have how many? 7 players. You have n players. Okay, and then there are conflicts. Let's say it's like this player doesn't want to play with that players. So when 2 player doesn't want to play in the same team with the other players, I add 1 edge. Okay, say maybe it's look like that. If you have these edges, the question is, can you divide the group of players into two teams, so that no 2 player in the same team has a conflict. Say, so for example, if you have this 3 edges, you cannot put this player in team 1 and this player is also in team 1 because they are in conflict, right? So one way to do that is that you maybe want to put this is the first team and this is the second team. Okay, you can see that there's no edge inside each of the team. Okay, now suppose that I add another edge, say this edge. Okay, if I have this edge, then this team is not okay, right? So you cannot have this team because these 2 players doesn't want to play with each other, right? But if you are trying to be a little bit clever, you can say, okay, let me include this guy in this team. Okay, this is the first team, and the second teams are these 3 people. Okay, so you can see that there's no edge between people in the same team, right? Okay, so the question is given a graph like that. So let me add a few others. Okay, can you divide the graph into 2 groups? Okay, so the question is this is like given a graph G with vertices V and HE. Can we partition V into 2 subsets A and B such that no edge between vertices in the same set? Okay, if you can do that, let's look at the picture. If you can do that, set A and set B, no edge in the same set, right? So there can be edges like that. So every edge would look like this, something like it has to go between the 2 sets. Okay, if you can do that, you need to answer yes. Okay, the graph for which this is possible is called bipartite graph. Okay, it's bipartite because you can separate into 2 parts. Bipartite is like 2 parts. Bi is 2, so 2 parts. Okay, if you can do that, then that's good. Okay, there are many other applications. You may think of dividing graph into 2 pieces as coloring. Okay, you want to say you want to color the vertices into into 2 colors. Okay, so that you want to assign the vertices into colors so that vertices with if there is an edge between 2 vertices, they have to have different colors. So this is like bi-coloring. So in this case, you can say I color this as blue and the red guy with this. You can see that for every edge, it connects red guy and the blue guy. Okay, so this is called bi-coloring or 2 color. two color or by coloring. Same thing, okay, two and by. Okay, so there are many tasks which look like that, but how can we solve this kind of task? Okay, so the idea is that I'm not gonna prove that it works. I'm not gonna prove the correctness of the algorithms, but the idea is that if you look at one vertex, if you say you need to put it in one of the two color, right? So if you put it in color 1, you know that if for all its adjacent vertices, this vertex has to be of color 2, right? And every other vertex that is connected with these guys, okay, has to be of color 1, right? And every vertex that is connected with this this set has to be of color 2, right? And so on, so on. You can use its argument to say, like, if there's a way to do bipartite, split graph into two parts or color the graph into two colors, you can see that it's the same thing, right? You can do that in this way. So you just give one vertex a color like red, and then every vertex that is connected to this one, you put it as blue, and then red, and then blue. If you can do that, there's one way to do it, right? Okay. And after this, you have a candidate coloring. Okay. Okay. So but if you look at this procedure, this is like basically breadth first search, right? So you run breadth first search so that these even layers are of color 0, and this odd level, these are of color 1. Okay, so this is the candidate coloring. Okay, and then you need to check if it works, right? So you need to check if there's an edge between the vertices in the same component or not. Okay, so if you check and there's no edge like that, then you get the two coloring. Okay, so the algorithm is basically like this. Okay, so the first step, you run breadth first search. Okay, and then assign vertices colors. Okay, based on the level. So color of U is going to be level of U mod 2. Okay, and then the third step, so this is the candidate. Okay, let me remark again, it's a candidate. So whatever graph you have, you can find this. Okay, this is a level from breadth first search, and then finally you check if color is valid. Okay, so basically for each edge UV in the graph, if color C equals color U, return false. So if it passed auto check, you say return. Okay, so that's the algorithms basically. There's a task that you need to do this. There are two tasks in the grader. Basically, you can just write one code to work for both tasks. It's pretty easy. If you get one done, you need to change a little bit to get the other done. The other task will be in UVA. Okay, so that's another application of breadth first search. So if you have your own breadth first search code, you can just do this task, these two tasks pretty easily. Okay, all right.